Howdy folks, this is a quick video on washers. Enjoy! A washer is basically a disc, but with a hole in it. Now how does this happen? Let's see. Let F and G be non-negative and continuous on A to B, and let R be the region bounded by above by F, below by G. And so here's how it would look like. So let's say I have A over here and I have B over here. And let's say I'm going to draw an f of x function like that. And a g of x function maybe like this. Okay. Well, the region that is between these two curves is what we are calling region R. And we're going to rotate that region about the x-axis. All right, so I'm going to draw the reflection in an effort to draw this. I'm going to draw the reflection, so like that. And then I'm going to draw a couple representative discs. Oh, but these discs are going to have a hole in it. It's kind of like a pineapple slice when the core is taken out. So here is one inside. Okay. And then here's like the one on the far right. All right, so basically what we have here is a circle inside a circle, like a washer, like a metal washer. All right, the big radius is going to go from the center to the outer circle, and on the graph, it's going to go from the x-axis to f of x. The small radius is going to go from the center to the inner circle, or on the graph, from the x-axis to g of x. So, to get the area of this middle part, the actual pineapple part, we need to do pi big radius squared minus pi little radius squared. So the volume is going to be the integral from A to B of pi big radius squared, and we said earlier that the big radius is f of x, minus pi little radius squared, and earlier we said that that is g of x. And then I ran out of room here, but dx. Now what is dx? dx is the thickness of this slice. And so let me thicken this right here in the middle. You can kind of see me thickening one of them. Now, the thickness runs this way. You see how my red arrow is going left and right? That is representing the thickness of that washer. Well, if it runs left to right, then it's a change in x. And when it gets smaller and smaller, it becomes dx. So it makes perfect sense. Let's look at example 4. Find the volume of the solid generated when the region between the graphs of f of x equals 1/2 plus x squared and y equals x over the interval 0 to 2 is revolved about the x-axis. So let's draw a picture. Now, f of x is something that looks like that, okay? And y equals x is something that looks like this. And so this yellow region is what we are rotating around the x-axis. All right, so to draw it, I'm going to try to draw the reflection. And I'm going to draw some representative discs or washers now because they have holes inside. I like to usually draw the inside circle first, but it's up to you. All right, so that kind of looks like, I don't know what that looks like a thing with a hole inside. Okay, all right, like a funnel maybe, but with a hole inside of it. Anywho, this time, the volume is going to be the integral from 0 to 2, because this is a 2, of, remember, pi big radius. So the big radius goes from the x-axis to this outer graph, which is f of x equals to 1/2 plus x squared. So that's going to be 1/2 plus x squared squared. Okay, minus pi little radius. So the little radius goes from the x-axis to this y equals x graph. So it's going to be x squared. And once again, I've run out of space, but there should be a dx right there. Okay? We're not going to evaluate this by hand, but this is the setup. Okay? Pi big radius squared minus pi little radius squared. Big radius is here, little radius is there. Okay? Now, the pi can be factored out if you want to. All right, let's look at example 5. Let R be the region bounded by y equals 1 over x, x equals 2, and y equals 2. Find the volume of the solid generated by revolving R about the y-axis. So first, let's draw this to see what region we're talking about. 1 over x looks like this. Here is 2, so x equals 2 looks like this. And here is 2 on the y-axis. And y equals 2 looks like this. So the region that we are looking at is this quarter circle looking region. It's not really a quarter of a circle, but it's this region right over here. Okay? All right, and we're going to rotate this about the y-axis. So to draw it, I'm going to try to draw the reflection. And I'm going to now draw some representative washers. Okay? And so I'll just draw that one washer for now. Now notice that the thickness is what I'm thickening right here. And this red arrow here is showing how thick this washer is. And look at my red arrow, it's running up and down. So it's a change in y. So this thickness is delta y, which you know that will become dy. Now this time the big radius runs from the y-axis all the way out here to x equals 2. And notice that every single one of these is going to be x equals 2. So the big radius is going to be always 2. But what's going to be different is the little radius. The little radius goes from the y-axis to this curve right here. And so this curve right here is y equals 1 over x. But everything is in terms of y. So you have to turn y equals 1 over x to x equals 1 over y. So the small radius is 1 over y. All right, so now we're ready to set up our integral. It's going to be pi. This time I'm going to factor out the pi. Okay, so it's pi big radius squared minus little radius squared. And like we said earlier, the thickness right here is delta y, and so this is going to be dy. Okay? Now we are missing the limits of integration, but these are y values. So I have to figure out what this low y value is down here that I'm marking in yellow, and this upper y value, which we already know is 2. So we already know that up here is 2. But what's that down there? Well, that is the intersection between, like right here, is the intersection between 1 over x and x equals 2. So we are trying to find the intersection between 1 over x, or y equals 1 over x, and x equals 2. So you can think of it like a system. So I can substitute this 2 right in there, and I'm going to get y equals to 1/2. So this is y equals 1/2, which means this lower limit is 1/2. Okay? So this right here is the setup. Okay? All right, that's all for this video. Bye-bye.